Greetings, statistics scholars, and welcome to this first video in our series from section 6.2 dealing with inference regarding population means. In this video, we'll be taking a look specifically at the subject of hypothesis testing for population means. Sometimes we have a research question involving the unknown parameter mu that we want to deal with. Let's take a look at one such question here. This is coming from exercise 121 in chapter 6 of our locked text. The research question here has to do with brains. Specifically, the question is, do autistic children have more neurons, on average, in their prefrontal cortex than 1.15 billion, which is the average value for non-autistic children? Well, to help deal with that question, researchers took data from a sample of 7 autistic male children whose ages were ranging between 2 and 16. What they found when they analyzed those brains was that the average neuron count for these 7 autistic children was 1.94 billion, with a sample standard deviation of 0.5 billion neurons. So we're interested in, do we think the answer to this question is yes or no? To get started, we must begin by writing the hypotheses that we wish to test. In this case here, the null hypothesis would be that mu, the average number of neurons in the prefrontal cortex for all autistic children, is 1.15 billion. Against that, we're facing off the alternative hypothesis that mu, the average number of neurons in the prefrontal cortexes of all autistic children, is larger than 1.15 billion. Now, to help decide whether we think there is evidence for that alternative, we have a sample statistic. Our sample statistic is that for our sample of size 7, the average number of neurons in the prefrontal cortexes of these children was 1.94 billion. That was our X bar, our sample mean value. Now, that is obviously larger than 1.15 billion, but the question is it significantly enough larger for us to find evidence for the alternative hypothesis? To begin that investigation, we need to get a handle on what the standard error for our sample statistic is. We learn in section 6.2 that to estimate the standard error for the sample means, we use the formula standard error equals standard deviation divided by the square root of the sample size, S divided by the square root of n. Now recall that in this research, there was a sample of size n equal to 7 and a sample standard deviation of 0.5 billion neurons. So using those values in the formula, we find our estimate for the standard error to be 0.5 billion divided by the square root of 7, which turns out to be about 0.189 billion neurons. We're going to use that estimate for the standard error of the sample means now to help compute something that we will refer to as a t-statistic for this hypothesis test. Standard error is about 0.189 billion neurons. Now, using that, we're going to compute something called a t-value. We're going to compute here, as we always do, the value of the statistic minus the null value divided by the standard error. In this case, that's our X bar, our sample mean, minus our mu sub 0 divided by the standard error. Mu sub 0 here refers to our null value. It is the average number of neurons in the null hypothesis, which is 1.15 billion. And we'll compute out this quotient here. But we want to take a note that we're going to give this quotient a slightly different name than we've given it in the past. In the past, we've referred to this quotient as a z-score. However, historically, it's been noted that whenever we compute this particular statistic, because it was computed by using an estimate for the standard error that involved using the sample standard deviation rather than the true population standard deviation, the distribution of these statistics, while still being symmetric and bell-shaped, these distributions have been noted to have fatter tails than the standard normal curve does. So because of that, we give these distributions a slightly different name. Rather than calling them z distributions, which is our name for the standard normal curve, we're instead going to call the distribution of these statistics t distributions. And the value that we compute here will be labeled a t-score rather than a z-score. Well, what is our t-score here? Well, substituting in x bar equal to 1.94 and mu sub 0 equal to 1.15 and a standard error of 0.189, and these are all in billions of neurons, we come up with a quotient of 4.18. 4.18 will be the t-score for this hypothesis test for our population mean. And we'll now use that t-score to help find a p-value that will determine the outcome of our test. We always finish off by finding a p-value. Recall that by p-value, we mean the proportion of samples that would be expected to give a result that's as or more extreme than the one that we just obtained. That's what we mean by the p-value of our test. Now, how will we find that here? To get the proportion of samples that are more extreme than ours, because this was a right-tailed test for a mean, we're going to look for the area beyond or to the right of our t-score underneath a t-distribution curve. And here we see to the right a picture that comes from StatKey from using the t-distribution app. Here we've used a particular t-distribution curve that we say has 6 degrees of freedom. In our case, our sample was of size 7, and that means that this particular scenario has what we refer to as 6 degrees of freedom. When we use the t-distribution with 6 degrees of freedom, and we look at the right tail, changing the cutoff value to 4.18, StatKey reports to us that the area that is to the right of the cutoff of 4.18, with this t-distribution with 6 degrees of freedom, we find a p-value of only 0.0029, a very small area indeed. And now that we have that p-value, we can decide the outcome of our test. We'll use our standard philosophy. We compare our p-value to the significance level of the test. We remember that when p is so small that it's less than our significance level, then we reject the null hypothesis, finding evidence for the alternative. However, if our p-value is larger than the chosen significance level, in that case, we would fail to reject the null hypothesis, deciding that there was insufficient evidence for the alternative. Now, here's our hypotheses again, and here is the comparison. If we use a standard significance level of 5%, our p-value of 0.0029 is definitely smaller than that significance level of 5%. Our value that is less than 1% is certainly less than 5%. So here, we will reject our null hypothesis. What does that mean? That means, in conclusion, that we have found evidence for the alternative hypothesis. Because the p-value was less than alpha, we conclude that there is evidence that the average number of neurons in the prefrontal cortexes of all autistic children is indeed larger than 1.15 billion. This has been an example of performing a hypothesis test for a population mean. And our next video will turn our attention to confidence intervals for population means.